Hi everyone. So today I'm going to be discussing the drug fentanyl, which is a synthetic drug known for its high potency but is used for many different medical purposes. So I'll be covering where we get it from, some of its properties including its structure, its ADME, which is how the body processes it, and its mechanism of action, which it uses to produce its intended effect. And then we'll finish off with a case study of an accidental overdose, and we'll see how plausible this event seems given what we find out about the drug. So in 1953, a chemist named Paul Janssen became fascinated with the idea of creating the most potent narcotic analgesic possible. He specifically wanted to experiment with synthetic drugs, and he selected meperidine, which is a synthetic drug derived from another synthetic drug called phenylepyperidine. And he selected meperidine because it's 30 to 35 times more lipid soluble than morphine, and lipid solubility is important for blood-brain barrier penetration, which is necessary in analgesics to produce the effect in the brain. And so what he did was he took meperidine, the compound seen on the left, and he added a phenyl group and a hydroxy group. The phenyl group is to help with lipid solubility, and that produced phenoperidine, the compound in the middle, which is about 200 times more potent than meperidine. And then some final configurational changes led to fentanyl, the compound on the right, which is about 100 to 300 times more potent than morphine. So now for some of the physiochemical properties of fentanyl. It has a very high log P of 4.05, meaning that it is highly lipid soluble and will easily diffuse into fat stores in the body. It has a pK of about 8.99, meaning that it's a weak base, a molecular weight of about 336 grams per mole. It travels throughout the body, very highly bound to plasma proteins. It has a melting point of about 85 to 87 degrees Celsius, meaning that it's solid at room temperature, and its solubility is about 0.74 milligrams per milliliter. Fentanyl has an extremely high potency, which is desirable among medicines to make them more safe, as just 100 micrograms will produce an effect equivalent to 10 milligrams of morphine. In terms of its therapeutic use, fentanyl is typically administered via IV, intramuscular, transdermal, intranasal, intrathecal, or buccal routes. It's uncommon to find oral tablets or powders due to its extensive first-pass metabolism. In illicit administration, however, people will typically use a buccal tablet or sublingual tablet or a transdermal patch. All of these methods help it diffuse slowly over time, which prevents overdose. However, sometimes it's sold as heroin or mixed with heroin, leading to overdose, or cutting of transdermal patches to produce a faster high will actually cause too much to be released at once, leading to overdose. The LD50 of fentanyl is very low, with experiments showing it to be just 3.1 mg per kg in rats and 0.03 mg per kg in monkeys. In this figure, we can see a lethal dose right next to a penny, showing just how small it is. The TD50, by contrast, is 280, which is very high, meaning that the lethal dose is significantly higher than the therapeutic dose, so it's considered safe for medical use, though easily becomes very toxic if it's used incorrectly. So now we'll move on to the pharmacotoxicokinetics, which is what the body does to the drug in the form of ADME. So we already discussed absorption. We know that it's best absorbed via IV, IM, ID, IN, IT, and buccal routes, and that oral administration is not ideal due to its extensive first-pass metabolism, which actually reduces the bioavailability to 0.31. In terms of the distribution, the volume of distribution for an IV administration is 4 liters per kilogram, which would be about 280 for the average person. Meaning that it would distribute to the plasma, extracellular fluid, intracellular fluid, and muscle. For oral administration, by contrast, the VD is 25.4 liters per kg, which would be 1,778 liters for the average person, meaning that it would also distribute to the fat. I also mentioned earlier that fentanyl is highly lipophilic with a log P greater than 3 and will cross the blood-brain barrier as well as the placenta. In addition, 80 to 85% of fentanyl in the blood will be bound to plasma proteins. I will now discuss the metabolism of fentanyl, whether it's an oral dose that undergoes first-pass metabolism and travels directly to the liver from the GI tract, or it's any other type of dose that circulates through the bloodstream and then makes its way to the liver. Fentanyl in general will undergo the same phase 1 and phase 2 reactions in the liver. Figure 2 shows many of the phase 1 metabolites formed with the help of CYP450s. For example, CYP3A4 forms the major product, an inactive des-phenethyl metabolite known as norfentanyl, via oxidative end-delocylation, and that's seen at number 2 on the diagram. Another example is despropionyl fentanyl, seen at number 4 on the diagram, which forms via carboxamide hydrolysis. Many other minor products are formed by hydroxylation of the compound, just at different regions on the molecule. These phase 1 metabolites are slightly more hydrophilic than the original fentanyl compound, which will later aid in its elimination from the body. Additional conjugation reactions may be performed to further increase hydrophilicity of fentanyl or its metabolites. These include glucuronidation, in which glucuronide conjugates are formed using glucuronidyltransferases, and sulfonation, in which sulfate conjugates are formed using sulfotransferases. Additionally, some phase 2 reactions involve further oxidation or methyl conjugation of phase 1 metabolites. We will now move on to elimination of fentanyl from the body. A small proportion of products will remain lipophilic and will be trapped in fat stores or circulate around the body for a long period of time before eventually becoming eliminated through the kidneys, and to a lesser extent in the bile and feces. Phase 1 metabolites undergo renal elimination, including products like norfentanyl and despropionyl fentanyl, whereas phase 2 metabolites, including glucuronide and sulfate conjugates, typically undergo renal elimination. Fentanyl's half-life varies significantly by the route of administration, being as short as 2.5 minutes for an IV dose and as long as 3 to 12 hours for a transdermal dose. Now we will discuss fentanyl's mechanism of action in the body. Fentanyl is an agonist, or a substrate that binds to a given receptor to produce a response. It acts preferentially on mu-opioid receptors located around the spinal cord. These receptors, when bound, initiate a signal transduction pathway that eventually signals to the brain to produce an analgesic effect, contributing to its medical use as a painkiller. However, its binding also induces dopamine production, which plays a large role in its addictive nature. Given that it binds to opioid receptors to produce a response, we can imagine that treatment of an overdose would require outcompeting fentanyl for the same receptors with a harmless substance. This is precisely how the substance known as naloxone works. Naloxone is an antagonist which binds to the same mu receptors as fentanyl without producing a response. It essentially inhibits fentanyl's ability to bind and must be administered quickly and in high doses to ensure that it can outcompete fentanyl before it is able to bind. Its brand name is Narcan, and it is commonly used to treat many suspected opioid overdose situations in the same manner. Now that I've covered the basics of fentanyl in the body, we're going to look at a case study in which a Stanford student was killed by accidentally overdosing on fentanyl after consuming fake Percocet pills. This student illicitly obtained what he thought was prescription Percocet for pain relief, though in reality they were counterfeit pills laced with an apparently lethal dose of fentanyl. Upon analysis, we'll find this situation to be extremely plausible. One tablet can easily contain a lethal dose of fentanyl due to its extremely high potency. With an LD50 of 0.03 mg per kg, a fatal dose for a typical 70 kilogram person would be as low as 2.1 milligrams. For reference, a typical Percocet tablet weighs about 330 milligrams. The tablet would have to be laced with not even 1% fentanyl to be lethal, and even when we account for first-pass metabolism from an oral dose. In addition, counterfeit-laced opioids are unfortunately in extremely high circulation and are often visually identical to legitimate prescription drugs. Figure 3 shows a typical counterfeit oxycodone tablet, which is imprinted with the same identifying M30 symbols as a legitimate tablet. According to the DEA, which uses a special laboratory to test the amounts of active ingredients in fake drugs, 26% of the pills come back positive for fentanyl in fatal dosages. This is a shocking reality that paints a very clear picture of the dangers of illicit drug use caused by fentanyl alone. I'd like to conclude by highlighting how fentanyl as a compound can demonstrate to us the nature of drugs as a double-edged sword. While its safe implementation into medicine has been approved due to its high potency and therapeutic index, illegal practices can quickly escalate into dangerous or lethal situations. I hope that this presentation has helped you understand fentanyl's discovery, properties, pharmacokinetics, and mechanism of action. Additionally, I hope it has demonstrated the importance of relying on medical and scientific professionals for the creation and use of safe drugs to be used only when needed. Thank you very much for listening.